Hi, I'm Stefan Bökelmann, the organizer and host of the emBO++, the next level conference for embedded system developers. And thanks to Zega, you can watch this video for free.
Okay. Hi, my name is Marek, and in this presentation we will be talking about an architectural pattern for embedded systems, a novel architectural pattern and a quite interesting one, at least at least for me. So, who am I? I am a C++ programmer for ages already. I started up with networking protocols and then did much client server systems. After that, I moved to Qt and user interfaces programming. I started out with Linux, then I did Windows, and then now I'm doing Linux again. And recently, I'm also doing more embedded work. And I'm a freelancer. You can hire me. If you don't hire me, then read my book about Qt performance. So, but let's start with the presentation, because this presentation is about software architecture. We'll start on a rather high note and discuss the notions of order and chaos. What is order and what is chaos? I have a garden. If I don't work in my garden hard enough, then the garden will be a mess. It will descend into chaos. It will be ugly, and I won't like it. So if I want a nice garden, I have to put some work into it. If I need a garden like such on the left side on the slide, I have to work hard. And what has garden to do with architecture? Well, the natural state of garden is wilderness, and natural state of software is chaos. If we don't work on software architecture, if we don't try to groom our software, it will inevitably descend in chaos. So the architectural work is really needed, and we shouldn't forget about it, because it's maybe not so interesting. Okay. So in this talk, we are not discussing general software architecture, but a single architectural pattern. And what is an architectural pattern? You all know what the design pattern is. And well, architectural pattern is something different. I like this definition from MITRE Systems Engineering Guide, that an architectural pattern is a method of arranging blocks and functionality to address a specific need. This means we have already partitioned our system in blocks, and now we have to find the right places for the right blocks. And again, what is a good pattern? Because there will be good patterns and bad patterns, as with everything. A good pattern will show you how to use it, when to use it, and why to use it, and what are the trade-offs. Because engineering is all about trade-offs, isn't it? So, an example of architectural pattern from the field of city planning is the axis pattern. you see this long street and long line going through half of the city with buildings arranged around it and sometimes in right on it. It somehow looks good, and people like this pattern and this art of organizing city buildings. So what are architectural patterns in software engineering? Well, we won't discuss all many patterns here, but only the most basic ones, because we don't have time for that. So we all know layered architecture pattern, where we have several layers of functionality building upon each other. Okay, it's the most popular pattern. All enterprise programming builds on it. Microkernel pattern is something like let us say Eclipse, where the system provides only the core functionality and interfaces where plugins could be docked in and extend the functionality of the system. And the last one, which we want to mention, is an event-driven architecture pattern, where systems just react to events and generate events as well. Okay, I think it was nothing new. So and now we will change our topic to embedded systems and architecture. Well, embedded systems and architecture, it's somehow the question is somehow dizzying, because normally when you are thinking about architecting an embedded system, you think about hardware. What hardware do we have? What processor? What periphery? What kind of operating system I want be running on the hardware? How can I cross-compile it? How can I load it on the hardware? Which graphics stack I will be using, and how can I orchestrate software updates? Okay, it's all very these questions are very interesting and must be solved, but somehow the software itself, which will be running on such a system, is just left alone, just spoken as a one big amorphous blob of something which will be working, hopefully. Yeah. So if there is a software architecture, then it looks like these basic layered architecture we learned in enterprise Java programs. Only that we don't have database layer. Instead, we've got hardware abstraction layer. Then we have application logic, exactly like in enterprise programming, and UI, exactly like in enterprise programming, provided we have some display. But normally, okay, today, even embedded software needs fancy user interfaces. So one one only example I know about is the AutoSAR architecture. This architecture is pretty big, because if you are reading about it, it's vast documentation, but in its core, it's a layered application where, again, application layer is one big blob of software. Then we have some layers beneath it. First, the runtime environment, which provides an abstraction of services. ECU is an electronic computing unit. It can be everything. Mini microcontroller, controller, and application processor. So this will be abstracted here, microcontroller, abstraction layer, and okay, this is the basic software. It's just for me it looks like just like operating systems services in for example Linux operating system. And over basic software we have this runtime environment, which provides us with communication facilities, and in application layer our application will be running. So now let's have a look on an application layer. It's not really so unstructured, as I said at the beginning, but what we have are components. These grayish rectangles, these grayish rectangles here, these are software components. They are defined to have communication ports. As you see, here one communication port, another, here another component with another communication ports. Several software components may be running on one processor, one ECU, and on each ECU we have this basic software and this runtime environment providing communication services, and basis software providing just operation systems like services. What we have many kinds of ports, but I describe it used here only two kinds of ports. One sender receiver port. This port specifies a logic like which we also have in the observer pattern. That one software component provides some notifications about changes of some value, and there are many and another software components may register for it. And then we have client-server ports, where we have just the normal client-server request-response interaction. So this looks very, very nice, doesn't it? But, boom, yes. Such a distributed system where we just pass messages around and don't have any structure could be maybe suboptimal. Let me tell you a tale about QNX software. I worked on. So QNX is an embedded operating system, and at the first look, it's very interesting because we are using message passing architecture. This means we have many separate processes which communicate with each other by sending messages. We don't share any memory, and we are decoupled from each other. Well, not we. The processes are decoupled from each other, and the communication and the servers, the processes can be made stateless. I think this can't be bad. Okay, it it is a rather modern architecture pattern. Message passing. I implemented such patterns by myself in other systems, so I was just very interested how well this system would work in real life. Well, this system was running on a medical device, and a rather complicated one. And we have many problems with it. And unfortunately, our system design looked like this monster here. It was horrible. Everywhere there were messages which were swirling around, and nobody knew who was responsible for what message and what message will be going where. And then messages would be pushed further downstream somewhere. It was a mess. We had too many messages. We had too many modules. The responsibilities were unclear, and sometimes they were split between. One responsibility was split between two processes with unclear reason. Nobody wanted to work with it, and we have tried to do some bug fixes and some extensions for the system, but at the end it wasn't workable. We have to ditch it. So message passing alone and architectures like AutoSAR, when we just have some message passing mechanism, are not enough to bring order in our architecture. So, what is emma? Because this talk is about emma. Well, emma is a nice software architectural pattern I just recently came. Into contact with when working for one of my clients, and they use it internally. So I just asked if I am allowed to blog about it and tell people about it, and they agreed. Okay, but I won't tell any details about this client, and I hope they won't be offended. And I will still be working for them. Okay, what does the emma abbreviation means the first letters were chosen to define the basic characteristics of emma, of this pattern, of this architecture. E stands for event-driven, M for multi-layered, the second M for multi-threaded, and A for autonomous. Well, event-driven, what is event-driven architecture pattern? Okay, we have some events and event dispatcher, and we can register for events and receive events and raise events. Okay. Multi-layered, okay, then we have to expect some layered architecture. Okay, I would expect it too, because it's state of the art, or not? Well, it's very well known, let us say that. So it's very well known, and people won't have trouble to understanding it. Multi-threaded, well, okay, we allow multi-threading. And autonomous. Autonomous describes, pertains to modules in our software architecture which should be autonomous. This means they shouldn't have too many dependencies. This is a very simple explanation, but we will explain it in more detail later. So, for what type of embedded systems is this architecture was this architecture planned? Low power 8-bit MCUs aren't the target. The target are this middle class Cortex M 32 bits MCUs which can run at LTIOs on it, real-time operating system. What about Cortex A class processors running Linux? Well, we will have a look at it later, but it could be a good target for it too. Our motivation for this architecture, how did this architecture come into being? Well, emma Software Architecture Guide document says that repetitively found issues found repetitively in earlier project were a major motivation for developing emma. So what were these issues? Well, I guess you will recognize some of them. For example, issues like solving the same task again and again, but in a different way, because the solutions done before aren't portable and aren't reusable. Then dependencies and cyclic dependencies, which render modules untestable. If I have too many dependencies, I can't write so many stubs and mocks. Okay, I could do that, but I'm not very keen to do this, and the testing of the modules in separation becomes very difficult. So then the classic that modules often are using several modules from different layers. So we can understand it in two ways. Firstly, that a module uses 3 modules from underlying layer. It shouldn't. It's too much dependency. It introduces too many dependencies according to architecture authors. Or the second way in which we can understand it is that a module is using other modules from different layers, not only from the next one downstream layer. So major problem in many, not only in embedded software development, is that control flow, system structure, and the ideas which shape the system design are not easily recognizable from the source code, from a cursory look on the structure of our project and on the names of the classes or functions or files and modules. The same with the communication patterns and asynchrony. Asynchronous communications and interrupt service routines are not easily found in the code. There isn't a special, normally there isn't a single special place designed for it. And we have just really read the code and know the code good, and then we will find that this function is used in an interrupt context, and this one is fires and asynchronous communication. So it would. So these make reading the code of the system difficult. Well, the next point the authors were pointing out is that we have a wide unstructured threading across all of layers, and it makes it very difficult to give some guarantees, some correctness guarantees for the system. Well, on the last point, yes, I said it already, that the dependencies are making modules untestable, but on another level, the entire architecture is normally not designed with testability in mind. It means not only any single module should be testable in isolation, but also greater chunks of the architecture should be testable too. So after we just listed all the problems of software development known to man, now we want to solve these problems. We can't solve anything, of course, so then we have to set up some goals, which we will try to achieve. So the goals of EMMA architecture were 1, 2, 3, 4, 5, 6, 7-fold. First one was a clear assignment of specific tasks in a hierarchy level, so that a programmer will know what to expect in this layer and what to expect in that layer. Second goal, also readability connected, is that we can comprehend our control flow even across interrupt and thread boundaries, so that we somehow can follow it from the code structure, and from code's naming, from naming of classes and functions. Of course, we want isolation and encapsulation of tasks and properties and modules. It's just a goal that can't be, which is modern and won't go away. So we will support it. Improved maintainability of code. Okay, this is connected to first points. Readability and comprehensibility. Improve reusability of modules between projects. Yeah, we would like to have this. If we minimize the number of dependencies, we can achieve it. So stable parallel processing by enforcing thread safety and interrupt service routines restrictions. So, well, threading is hard. Asynchronous processing is hard. Interrupts are asynchronous. So we need some restrictions and some boundaries and some guidelines to diminish our freedom of choice in this area, but which will then result in correct programs. So, and the last point is, of course, high level of testability, and it will come with reusability, I think. So, of course, we have always to pay our price. What price are we willing to pay in order to achieve these highly goals? First, okay, we have to be prepared that some empty forward-only modules might be required to keep the layer structure. Then, because we have this prescribed layering, then putting up a new project and and structure of new project structure and directory structure will be more difficult. Then, if we have boundaries and guidelines, it will require more discipline when designing and coding. It's not just I'm not just that cowboy which can do what he wishes. I have to respect some rules. But okay, most programmers are used to it now, I think. And the last problem or last trade-off, that such a structure, when we partition our software in several layers and then pass data between layers, that this requires more processing resources. But we already stated that our target platform aren't the 8-bit low power microcontrollers. So I think we can afford it. So, which software designs wants emma to avoid? Well, what we don't like are cross-layer calls. These are these orange arrows here from the module on the left, on top left module, which are calling modules in our layer, in our core layer, and then in the hardware abstraction layer. In a layered architecture, it's a no-no. Layering is normally should normally be pretty strict, and the layer can only communicate with the layer next down in the hierarchy. Intra-layer dependencies, like these red arrows between two modules. Why are these bad? Well, they can lead to cyclic dependencies, which we see here in depicted with blue arrows. But not only on the other side, they are bad because we are increasing number of dependencies for a module, and decreasing the quality and the testability of the design. So, okay, and the last problem we want to avoid is unrestricted threading. So modules with here unrestricted threading says that that the modules can use multi-threading in every layer they want. Why is that bad for our design? emma authors say that no, they just say it is bad. They said we need some guidelines, and it's not so important what these guidelines are, but that there are some guidelines pertaining threading at all. So for emma architecture, we will choose a set of matching guidelines. So software architecture we want to avoid are like this. Here, our system design a monster and dependency swirling around it everywhere. Like on this picture on the left, where each module is talking to another module and then back to a module in layer above and down and 2 layers down. So at a point, you won't be able to say what the system is doing and how it is working, what the idea of its operation is. So the authors of emma architecture took inspiration from the 7 layers of OSI model. You probably know what 7 layers model is. It's a layering architecture. As we already said, emma is a layered architecture. So some layers had to be defined, but the ingenious idea in this architecture is that we could take inspiration from this 7 layer model and transfer it to the structure of the code running on a microcontroller. What layers have we defined in the 7 layers in the OSI architecture? So first is the physical layer. This physical layer just sends bits over the wire. It's doing just transformation of bits into electrical signals. Data link layer sends builds on the capacity of physical layer and sends data between two ends of.
Wir sind hier in einem kleineren Grossraumbüro.
Bei den Leitern habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Leica Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
The wire. So network layer takes this possible and okay, between two, not really. It knows the binary structure of the data. Network layer sends this data. Can send data from one network node to another, from one router to another. And transport layer takes this network route and sends transports data from one user of the network to the next, to the second user of the network, so they can communicate. The session layer provides a session between these two users. It means it defines some protocol, how they talk to each other. Then the presentation layer is about encoding and decrypting and the application layer is just about building some applications using communication we have defined in our communication stack. So how does this transfer to software architecture? Well, we have 7 layers. We have defined 7 layers, and they are correspond to 7 layers of the OSI model. The first layer we have in OSI is the physical layer. In the M architecture, we have the driver layer. Driver layer uses provides access to hardware. Using libraries, or implementing these hardware access by itself. The second layer is data link layer. Data link layer communicates between 2 points, and in the M architecture, the corresponding layer is called periphery, and it abstracts the hardware, and it provides an interface for some hardware with operations we defined for the abstraction of this hardware, like read, write, send, receive, and configure, things like that. So I don't really see a clear connection between the periphery layer and data link layer. Well, it's also more abstract than just a physical layer where the driver resides, but okay. It's maybe not that obvious. Then we have the interface of the hardware access layer, and here now we provide not only access to single periphery devices, but we see the peripheries as a service provider. So it's even higher layer than this hardware abstracting hardware in HRL level 2. Okay, next layer. These 3 lower layers are hardware access layer. They are called hardware access layers or hardware abstraction layers. And the next 3 are our core layers. Core layers could be also named logic layers, because it is where our logic of our program resides. First, we have layer 4 transport, where we define services which are responsible for specific parts of system. We will see some examples of such controllers soon. The workflow layer builds over the controller layer, and it provides some scenarios, longer scenarios of interactions for some device or group of devices or several devices. And here the corresponding session layer of OSI model is a very good match, because it also defines some scenarios, some conversations, types of conversations which can be taken. Core interface is the 6th layer, and it provides command interfaces, exports command interfaces for all our core modules, for all our application logic. And the 7th layer, application layer, is just the way in which we interact with the outer world. It could be a message loop waiting for commands to come in. It could be a GUI. could be just a fixed command sequence. So it is the top layer of which drives our complete software application. So, overview, we have layers. The building parts of emma are layers, elevators, and other things. Layers, we have already discussed layers. Then we have elevators. What are the elevators? Okay, these are software components which implement event propagation, because the layers only can reach down this stream and can never propagate any information to a layer which is positioned upstream. For this, we have our elevators, which will send events, which will define events, and software components may register and then will be notified when these events are raised. And last part of the model is infrastructure and utility modules, which we see here on the right side of the picture, and every layer may access it because it's general. These are general modules. What rules are defined in emma? Modules should be autonomous. This means that they are only dependent on lower modules, and they can work standalone once lower modules and elevators are initialized. Modules input come from an upstream module or from an elevator, as we already discussed. Modules output goes to a downstream module. So the only way is down, down, down. All interrupts are transported over a single elevator. Over a single elevator in this HL elevator module. All events are transported over a single elevator in this core elevator module. And last rule, we have naming conventions. What isn't part of emma? Okay, we couldn't, you can't solve everything, so we don't solve error handling. It has to be defined separately. Data persistency, data structures, message formats, we don't do that. User interface is normally not part of emma, but okay, we will try to extend the model to use user interface. Then maintenance, upgrades, and internalization. So we don't have many time left. Okay, threading. What are threading guidelines we have to observe? On the hardware abstraction layer, we don't do any threading. It's as simple as that. We do threading only in application and core layers. So we have naming conventions. So if we then have a look on an application using emma architecture, then we see right away, here's our application layer, here is our here are our common utilities. Here we have our core layer with controller, elevator, and with sublayers and elevators. Here we've got our hardware abstraction layer with three sublayers and elevator. So we have Also naming conventions. Yes. So naming conventions, don't have time for it. Module examples, control flow. Startup is the only module which can which can access all modules in any layer. But in reality, this is a wonderful architecture, but in reality, it can't be a good fit for everything. So users are always free to deviate from emma. Discussion, no time for it. Use case 1. Bootloader on a device control MCU. So now we have something a little more concrete. So in the application layer, we have just a message loop thread. This message loop will wait for inputs and react accordingly. So what could be the inputs? The inputs could be a request to do a software upgrade, or a request to reverse some software, things like that. Then next layer, we have our interfaces, which application layer is using high layer abstractions for CAN interface, console interface, workflow, controllers, hardware abstraction layer, everything we discussed already. So elevators can be just implemented like simple callback tables. Startup, as I said, in doing startup, we can access every layer, every module from every layer. So we start just, we begin with layer 1 modules, then layer 2, layer 3, and so on. So this was something different. Use case 2, target tests on device. Yes, we can do that. Also, the top layers will be replaced on device, will be replaced with target, with test layers, and then we just test our lower layers, our hardware abstraction layers. So the structure of such a program will be very similar to a normal emma application, as you can see here. We can also do the different the test other way around by using emulation for lower layers, and then our application layer will then receive test commands, and we can test our logic with some emulator. Use case 3, we don't have time for it. So, thank you. Are there any questions? So I wish that you always that your architecture is always so usable, yeah, like this one on the picture, and so well matching with the legacy systems, and that your users are so happy to use it like these people on that picture. So thank you.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.